So now that we have already seen Kirchhoff's current law, we're going to focus on Kirchhoff's voltage law. Kirchhoff's voltage law states that the sum of all the voltages in a loop are going to equal to 0. The sum of all the voltages in a loop are going to equal to 0. Something important to take into consideration here, or to have in mind, is that each one of the components of a circle is going to have a potential across them, a different potential across them. Voltage sources, such as this voltage source or this current source, are going to have an individual, independent voltage or polarity. So this voltage source is going to have its own individual independent polarity, and this current source is going to have its own individual independent polarity. Which, if you look at the drawing, it's always going to go like this, right? And now, the resistors, the other components in a circuit, are going to have a polarity that is going to depend on the direction of the current. So in this case, the direction goes here, and it goes in through the positive side, out through the negative side. That's how you assign the polarities. So you're going this way, this goes in through the positive, out through the negative. And then the current goes this way, and then it goes in to the positive, out through the negative. In situations where it is not that evident or that obvious which direction the current is going, you're going to make your best guess. And if by the end of the resolution of your circuit, any of these currents give you a negative value, it means that it goes in the opposite direction that the one you assumed at the beginning. Okay, so we're going to see here in this circuit, which is exactly the same one as this one up here, we're going to see Kirchhoff's voltage law in action. Here are the polarities that I already assigned up there. Actually, this one is incorrect, because we assumed that the current was going this way. So here are the polarities, and we are going to use Kirchhoff's voltage law. So we're going to prove that the sum of all the voltages in a loop is going to equal to 0. We're going to start here, and we're going to go up, right? So we go here, up to the across the voltage source, so plus 5 volts. Now we continue, and we go across this resistor. We're going from positive to negative. This is a voltage drop, so it's going to be, that's my cat sneezing, believe it or not. Bless you. Bless you. Oh my God, sneeze attack. So we went up here, and now we are going through this from the positive to the negative. That's a voltage drop. So minus the voltage across the 3 ohm resistor, which is this one. Then we continue here, and then we go down, because we're trying to complete this loop. So we go down, and then we go from positive to negative. That's a voltage drop. So minus the voltage across this is 1 ohm, across this 1 ohm resistor. And then if we continue, we would make it back to the starting point, so we say equal to 0. So how would we further develop this equation so that it helps us solve the system? We would use Ohm's law that states that the voltage across a component equals to the current across that component times the resistance in that component. So then here it would be 5 minus the voltage across the 3 ohm resistor. This is the current that is going across the resistor times the resistance. So let's say that this current, we're going to name it current I1. And then we would say I1 times 3 ohms, that equals the voltage across this resistor. And then this one is the voltage across the 1 ohm, so the current that is going this way, let's name it I2. So it's going to be the voltage across this resistor is going to equal to I2 times 1 ohm, which is the resistance of that resistor. You would do that for both of the loops, and then by solving the system of equations, you would be able to find the value for each one of these currents. So I said that we were going to see Kirchhoff's voltage law in action. And I'm going to show it based on this step. So 5 volts over here, the voltage across the 3 ohm resistor over here, and here I put 2 little probes that are actually measuring the voltage. So this would be 5 volts minus 3.375 volts. And then we continue, minus the voltage across the 1 ohm resistor would be minus, and we see here with the little probes that I put, that is 1.625 minus 1.625 volts equals to 0. These two, you're going to realize that if you add 3.375 plus 1.625, it's going to equal to 5. So this is going to end up being, and I'm going to do it just in case to prove it, 3.375 plus 1.625, and it equals exactly 0. So this is going to be 5 minus 5 equals 0. And we see that voltage, Kirchhoff's voltage law happens here, like complies. It occurs. We can prove it. And that's how we see Kirchhoff's voltage law in action. This is 5, and then you will add this, and it will be 5. So obviously, plus that voltage minus that voltage will equal 0. You will see exactly the same thing in this other loop. You will see that plus the voltage across this resistor will be equal to this one and this one. Those 2 voltages added. So you see that if you go up here, you are going to say plus the voltage across the 1 ohm minus the voltage across, plus the voltage across this one minus the voltage across this one. So then you will see that that is 0. We're going to do it. So remember, starting here, going up, plus 1.6250 volts. Remember, this is the voltage across the 1 ohm resistor, which is this one here. We continue over here, and we have plus 1 volt. And then we continue over here, and then we have minus 2.625 volts. If we solve that, we would see that it's equal to 0. So the reason why this one, here I put 1 volt and here it says negative 1 volt is just because I put the probes the other way around. So this is a positive one, this is a negative one. I should have put this one over here and this one over here. And then it would give me positive. Why should I put this one over here, this one over here? Because the current is going this way. So this side would be the positive, as this marks over there. Okay, so that is Kirchhoff's voltage law. And that is the basis of the classical method, what is called the classical method. So for the classical method, you use Kirchhoff's voltage law across each loop to get to the answer and to solve for each one of the currents. I hope that helps.